Bismillahirrahmanirrahim. Today we will discuss blood pressure measurement. First of all, pressure at the heart. Force of contraction of the heart is acting tangentially at the surface. You see, this gives what we call a tension, which is force per unit length. So according to Laplace law in a sphere, P equals 2T over R. So whenever we have a distended failed heart, we have the radius increase. So we must increase the tension by the increase of the force of contraction of the heart by hypertrophy to yield the same pressure according to the equation. Mean blood pressure equals, of course, the peripheral resistance times the cardiac output. See? And mean blood pressure equals the diastolic pressure plus 1/3 of the pulse pressure. Measurement of the blood pressure, the simple, of course, the non-invasive method of inflatable cuff recording to a monitor. The cuff must be positioned so that the center of the bladder in the medial side over the brachial artery. The width of the cuff must be 20% greater than the diameter of the arm. You see, we'll show it in a bigger figure. So the width is 20% greater than the diameter of the arm to get a proper measurement. The monitor, of course, is a mercury manometer. The zero must be correctly positioned, not inclined, but if it is calibrated to be inclined, well and good. Of course, partial blockage of the airway may lead to sluggish readings, and the upper part filter must be removed to clean the dirt accumulated upwards. Of course, we can use Android gauges, but the problem that they must be calibrated every now and then. The detector, of course, we must release the pressure slowly, as you can see this rate. Whenever the systolic blood pressure appears, we can record it by special detectors. First of all, palpation by the radial pulse, auscultation by the corticoff sounds, the first and the second, third, the fifth, which is justified to be the diastolic pressure. Of course, we can use the pulse oximeter with the blood pressure, and we can use a microphone, audible microphone on the brachial artery. And we can, of course, use oscillometric system, and ultrasonic can be also used. The oscillometry, the first beginning, it was manually operated by what we call von Recklinghausen oscillotonometer. It is based on the oscillation of a needle. Whenever this needle amplitude is beginning to increase, it yields the systolic, and when it reaches its maximum, it yields the mean, and then it begins to slow down, indicating the diastolic blood pressure. First of all, in the past, it was constructed of two cuffs, peripheral and distal. Each of them is connected to a pillows, you see, and there is a system where I can direct whether I'm using the upper cuff or the lower cuff to reach to the oscillation of the needle, giving the pressure we mentioned before. Nowadays, of course, is automated. Instead of two cuffs, we have a single cuff with a pressure transducer where it measures the pressure and oscillation. Of course, the pressure signal it's analyzed by a transducer to give the three readings we mentioned before. The system begins first of all by increasing the pressure to 160 millimeter mercury, and then after that it increases the pressure by 5 millimeter above the recorded previous measure. Of course, the rate, as we said before, 2 to 3 millimeter mercury per second. Of course, the problem is that the continuous measurement impedes the blood flow. So the maximum is every 2 minutes whenever we have a problem that we are in need of continuous measure of blood pressure. Of course, is less accurate in the presence of arrhythmia and pressure below 50 millimeter mercury. Radial artery compression device is something like a pressure sensor strapped on the wrist, and then it increases hydraulically. The pressure sensor is driven by hydraulically mechanism, increasing the pressure over the radial artery, compressing the radial artery. And this fluctuation of the radial artery by an algorithm can estimate the diastolic and the systolic and so forth. And it gives a wave, pulse waveform. And it's very sensitive to motor artifact. By the algorithm also can dismiss this artifact. And it requires only from 12 to 15 beats to obtain measurement. Of course, we must carefully place the sensor over the radial artery. Other automated techniques, we have the microphone on the brachial artery. It, of course, it records infrasound, which are the sound which we can hear. And we can use, of course, ultrasonic transmitter using the Doppler change of frequency. Of course, all these are inaccurate whenever they are situation as pheochromocytoma, or whenever we want to use controlled hypertension or in a shock patient. So it's preferably, of course, in these circumstances to use a direct blood pressure measurement. The Mina's technique, it is like the oscillometry, automatic oscillometry, but it utilizes the finger. We call it fila press. It is a cuff applied on the finger. Of course, there is a transducer that measures the pressure, and there is an air pump and a servo control valve, of course, to control the pressure. Of course, it utilizes the changes in the oscillation of the needle, recording the three measurement types. And also it has an additional infrared entering diode using the infrared rays, creating what we call plethysmography. Of course, it records the volume of the arterial blood under the cuff, you see, and then it is processed to analyze the photoplethysmography according to the volume at a point set according to the mean blood pressure. So it is adjusted so that whenever there is a repeating of the blood pressure, it adjusts the pressure so that it will not lose the tracing of the photoplethysmography. You see, we'll show all these figures in a bigger illustration later on. Now we come to the invasive techniques. Of course, we use the radial artery first of all. It's the first choice, and then we must do what is called modified Allen's test to guard against the thrombosis. First of all, the hand of the patient is clenched into a fist, and then we occlude by the doctor to the two arteries, the ulnar and the radial, and then the patient relaxes clenched fist. And then the doctor releases the pressure on the ulnar artery, you see? So as if he's creating a scenario where the radial artery is being occluded by supposed thrombosis. The patient hand should be flushed within 5 seconds. If flush is delayed, that means that there is a bad recirculation or communication between the ulnar and the radial circulation, which will hinder or make it a problem. So whenever there is a problem, I can use, of course, to shift to the ulnar artery and change the way of the anaesthesia. Of course, we inject local anesthesia to guard against spasm of the artery. The candy should be constructed from Teflon to be short and parallel in size. We will tell you later why are this are specifications for a proper arterial cannula. Of course, we prevent thrombosis by continuous injection of heparin, and we never use syringes less than 5 milliliter. Otherwise, the artery will be injured by the force of the injection. And we can use what we call the intraflow, which is a system whenever we want a continuous prolonged duration of heparin by increasing the pressure to 300 millimeter mercury at a rate of 5 milliliter per hour. This is a method where we will show it later on. See, to continue inject the heparin. Of course, the final waveform procedure is going to be displayed on an oscilloscope or a recorder tracing. The blood pressure, of course, as you can see from the tracing, is more narrower and higher in whenever I go away from the circulation, which is again is the hydrostatic laws of flow. You see, but we must put in our mind the elasticity of the arterioles present there, where it increases the amplitude of pressure distally. More in the dorsal speed, it's more than the radial or the aorta. The arterial pressure frequency ranges from 0 to 40 hertz. You see, so the apparatus must be capable of adjusting itself to cope with this range. The amplifier and the recorder, as we will show you later on, have no difficulty in dealing with such frequency. The problem is the transducer itself and the connection to the cannula, where there is the arterial connection and the saline going to and fro through it. Now we come to the analysis of the arterial pulse configuration. We have what we call resonance and damping. As we said before, that the system of the recording of the blood pressure has a range of identification from 0 to 40 hertz. So whenever the catheter and the cannula, whatever, oscillates in such the similar range, it will interfere, calling what we call resonance. Resonance comes from the figure that whenever I make a hit weight connected to a spring and I leave the weight will go upwards and downwards in a frequency. We call it a resonance frequency. So to avoid the interference through the catheter and the cannula and the saline connectors, we ought to have a shorter, wider, and or stiffer catheters to avoid the interference of the causing resonance. Of course, if there is a restriction to that transmission of the blood pressure, or there is air or a thrombus, it will call what we call damping. The pulse pressure wave will be much decreased. Central venous pressure recording, as we can see, it records. Of course, we cannot indirectly measure the CVP, but we can notice the engorgement of the venous system. Otherwise, we use the CVP. Of course, we connect to the internal jugular, mainly the right side, and then we connect it to a saline, as we can see with the stopcock, and then we connect the CVP line with saline, and then we let the saline go down till it settles to a point where it gives a hint about the CVP. Of course, any invasive technique has a problem such as pneumothorax, hydrothorax, and of course the zero point is the mid axillary line. And we, of course, we use centimeter water, but if we have a transducer, we can use millimeter mercury, and then put in your mind that 1 centimeter water is about 100 Pascal, 100 Pascal. Venous pressure, the cardiac output. Of course, whenever I want to measure the cardiac output, I must, of course, I can use the right side measurement as using CVP, or the left. The left, whenever I want to use the left arterial blood pressure, I ought to use what we call the Swan-Ganz catheter, which is the catheter being introduced through the CVP, and by the pressure tracing, we can reach to one of the branches of pulmonary artery, where we are recording the pressure of the capillaries, which gives a hint about the left atrial pressure. You see, we have a balloon in the distal part of this catheter. Whenever it's inflated by 1 cc of air, it's floating. The direct current takes it to the pulmonary artery. Of course, we can, as we said before, notice the position of it whenever the pressure becomes widget like a pyramid, and this is the tracing of the arterial blood pressure through its journey to reach the pulmonary artery. These are some figures I will show. Of course, this is the tension developed by the tangential movements of the heart to create the pressure. You see, it goes tension. So force, tension means force per unit length. You see, not like the pressure. Pressure, as we know, is force per unit area. This is the different level of pressure in the human being while he is standing. Of course, the upper part of the head is 53, and in the position of the right atrium is 90, is the mean pressure, and in the lower limb, of course, that definitely more than the measurement of the upper limb, which is 150. This is the diameter, this is the width size, proper width size of the cuff, where it equals the diameter of the arm plus 20% of it. And this is of course the cuff, and this is the mercury, where we must take care of the filter upwards to clean it from the dirt. And this is the von Recklinghausen oscillometer, which was the beginning of oscillometry. We have 2 cuffs, and each cuff is attached to its own pillows. This pillows, of course, in the automated one is replaced by a pressure sensor, and we have a T valve which directs the flow to either one of them, and we have a leak valve. So this is the beginning of von Recklinghausen oscillometry based on the oscillation of this pointer. This is the automated method. Of course, this is a cuff which has the pressure transducer. It measures both pressure and oscillation, and we have a bleed valve to release the pressure, and we have an air pump. And this is, of course, the diaphragm and the strain gauge, and we have a microprocessor to process the data into, as we can see, different types of pressure measurement. And this is the Benaz technique, the FINA press, and this is the photo light emitting diode, and this is the receiving item, where it measures the blood volume of the artery, you see, and it goes to a servo control valve. This servo control valve maintains the photoplasmography to keep the tracing. You see, it increases to a limit so that it will not compress the artery. You see, we have an air pump, and this is the radial arc compression device where it compresses the artery between the radius and the subcutaneous tissue, and it is this pressure sensor is controlled by controlled hydraulically. You see, it increase the pressure, and it senses the fluctuation of the wall of the artery whenever it's deflated and inflated. This is the picture of the artery when it's compressed and it is non-compressed. This is the figure showing also. It makes the artery sandwich between the subcutaneous tissue and the bone. And this is the direct measurement of blood pressure. This is the radial artery, and this is the continuous measuring by pressure by 300 millimeter mercury, and we have a constriction to give 4 millimeter per hour for continuous. And this is the amplifier, and this is the transducer. You see the amplifier, of course, is drawn in a triangular. Of course, these are affected or could induce a frequency which enters the frequency of the normal blood pressure measurement, and will induce what we call resonance. This I forgot to tell you. This is the caster tip transducer, which we can measure arterial pressure inside the body, whatever pulmonary artery pressure or the CVP pressure. It's made of a mirrored diaphragm, and we have an incidence and reflecting light. Of course, this mirror is being by the pressure is being bound either becoming concave and it will affect the reflecting light. This reflection, of course, will give me a hint about the mechanical pressure increasing the configuration of this diaphragm. And this is a tracing of the different arterial blood pressure, whether dorsal speeds, as you can see, it is more peaked and broader, or I'm sorry, the width is decreased in comparison to the aorta. And this is the types of the normal blood plethysmograph, and this is how does it look whenever there is a resonance. It's damping. It's quite evident that it's lower than the normal, and this is how we measure the CVP, the stopcock, and the communication between the saline and the mercury column. I'm sorry, but CVP, and this is the position of the CVP and the pulmonary artery between the right heart and left heart. Of course, whenever there is a left heart failure, it's difficult to be discovered by the CVP. So we must have a pulmonary catheter to measure the pressure of the left atrium. And this is the pressure tracing whenever I go by the catheter. Of course, it's quite obvious the increased pressure in the right atrium. It becomes wedges. You see, it looks like a pyramid. These are the hint about the blood pressure. Thank you very much. Sorry for my mistakes. I hope that I did my job. See you later, inshallah. Wassalamu alaikum wa rahmatullah wa barakatuh.